Sup, everybody? Sorry I can't make it. Dealing with a little bit of emergency. Same thing as yesterday. But I should be back tomorrow. But making up for it, I have the next best thing, which is a video, me coming live to you through the power of the internet. Well, not live. I'm asynchronously doing this. But what we're going to need today to do this lesson, you're going to need your brain. Hopefully you didn't forget it at home. But you're most importantly, you're going to need a pencil and your book, which you might not have your book yet. So go get your book. Take a minute to go get it. Go. Okay, once you have these three things acquired, what we're going to talk about today is division, and in particular, polynomial division. Okay, I hinted at it last Friday. But let's just start off. Before we even talk about what we're going to do today, I just want to start off on the bottom of this page, M223 is what it is, M2-23, divide and conquer. On the bottom of page M223 in this little section, okay, we're not going to look at what it says. We're going to use this little section as just some blank space, like Taylor Swift. And we are going to long divide, just numbers, okay, which might be a little blast from the past. I know it's a blast from the past for me because you don't really use it once you have access, like unfiltered access to a calculator, right? You can just press the divide button. But it is useful, maybe, at least it's useful within the context of what we're going to do today. And maybe this is the reason why they teach it, so that you don't have to relearn it as a sophomore, or a freshman, or a junior in high school, right? So here's what I want you to do. I want you to go ahead and divide this for me. I want you to divide 12 from, or I guess, divide 12 into 3,660. 3,660 divided by 12, right? This thing. Okay. Give this a try. Give this one a try. I don't know if you remember how to do it. Maybe you do, maybe you don't. But give it a try. Work with the people around you. Okay. I'll give you 1 minute to divide 12 into 3,660. Okay, did you figure out how to do it? Did you remember? It's probably been a long time, okay? It took me, when I learned this thing that we're going to talk about today, polynomial division for the first time, man, did it really send me, like, I literally was sitting in my, like, Algebra 2 class in high school, looking up at the screen and I was flashing back into 5th grade, where in my 5th grade, my teacher, Miss Masteller, she like made us like we each wrote a digit into this number around the board in the classroom, and we each long divided a number into that thing. So it was like everybody working on this giant long calculation that went across the whole whiteboard. Anyway, I was like sitting in my Algebra 2 class as my teacher was talking, and I was just like reminiscing on that. So anyway, that's where I'm at right now. I'm also flashing back to 5th grade. But really, division in general is just all about how many times can this thing, we call this the divisor, go into this thing, which is our quotient, right? Went to our quotient, if you remember those words. So in other words, we're trying to figure out how many times can 12 go into 3,660, okay? Now, you could just type it into a calculator, or you could think about, I don't know, like you could do 12 times 100 is 1,200, and then times 3 is 16, right? We're going to do it the long division way, okay? The way that you were probably taught in the 3rd or 4th or 5th or 6th or whatever grade, okay? And it goes like this. You take your divisor, the thing on the outside of this little symbol, and you want to get this thing, you want to bake this into this number. And you start with the leftmost number, okay? So for instance, can 12, or how many times can 12 go into the number 3? Just this number to the number 3. Well, and that means evenly, right? How many times can 12 go into 3 evenly? Well, it can't, because 3 is smaller, right? So 0 times. 12 can't go into 3. So then you extend out one more. Then you say 36, okay? So I looked at 3, it was 0. Now I'm at 36. How many times can 12 go into 36? Well, it's 12, 24, 36. So 3 times exactly, which is nice, okay? So here's what you do. You then say 12 can go into 36 3 times. So you put it over the last number that you looked at. And then you do this little calculation underneath. And this is probably the tricky part that you had to remember, just sort of get the process back in your brain. You take this number and you multiply it into your divisor, and then you write that number underneath this, right? Underneath your quotient. And so you take 3 times 12 is 36, and then you subtract the line, all right? You subtract the line. So we were at 0 for the 3, 3 for the 36, and then we subtract 36 from 36 is 0, and then you drop down this number, 6, okay? So then you drop down this number. So once again, I subtracted this, and then I dropped down the next number in my quotient, and now I look, imagine I was doing it like this again. So we repeat this step. How many times can 12 go into 6? Well, 12 can't go into 6, so it can go in 0 times. And then we drop down this number, right? 60, okay? And now we think about how many times can 12 go into 60? Well, 12 can go into 60, 12, 24, 36, 48, 60. That's 5 times in total. So we put a 5 up top. 5 times 12 is 60. You then subtract these. And once you run out of quotient, once you run out of number in underneath your little sign here, this is your remainder. It's the things that are left over when dividing by 12. But in this case, because 12 can evenly go into 3,660, you end up with a remainder of 0, which means your answer is 3,660 divided by 12 is equal to 305. Nice. Okay. Little flashback, little blast from the past. All right. Let's do another one. Let's do another one real quick. I'll go a little bit faster just to practice it one more time. This is kind of fun, I'm sure a lot of you at some point in your mathematical career were very good at this, maybe racing against other people in your class. I'm going to come up with 2 numbers off the top of my head. I don't know if these go well together or not. Let's say 23, Michael Jordan, and 3,512. I would be surprised if 23 can go into that number, but I'm just making it up off the top of my head. All right, so then we start. How many times can 23 go into 3? None times. So that's okay. We skip that. And now we will look at just 35. You can put a 0 here if you want, but it doesn't change it overall, right? So now I'm just looking at how many times can 23 go into 35? Well, one time. And 1 times 23 is 23. So then we subtract, right? And so we're not ending up with an even thing this time. Instead, we're going to take 35 minus 23 is 12, okay? And 23 can't go into 12. So instead, we then drop the 1 down here, and we're looking at 121. So now our new question is, how many times can 23 go into 121? Well, 23 can go into, well, 23 is almost 25, right? 23 is almost 25. 25 can go into 100 4 times, which means that this is 8 less. So 23 times 4, it's got to be 92. And then can you add another one onto that? I think you can, right? So you can just say that 23 times 5 is another 23 onto this one, which would be 115, I think, right? 115. Yes. So to answer my question, how many times can 23 go into 121? 5 times. That is 115. You then subtract 121 minus 115 is 6. You then drop down the 2 that's left over here, and you say, how many times can 23 go into 62? Well, I think only twice, because you get 46, and then 46 plus 23 is 69, which is too big, and so we say 2. And 23 times 2 is 46, and then you subtract, and you get 62 minus 46 is 416, and that is your remainder. So you've probably written this, you would say 3,512 divided by 23 is equal to my number up top, 152, R16, right? You've probably seen that before, okay? And that would be another answer. The R stands for remainder, meaning how many left over that can't make it into 23, okay? Now what that means, the remainder theorem, which we will talk about tomorrow, is it's really 16 23rds, right? It's 16 parts out of the 23 that you were looking at. So it's really 152 plus this number, okay? Whew, anyway, there's some long division for you. Good old-fashioned long division. And the reason that we're going to talk about that, the reason why we're going to do it today is because we're going to describe similarities between polynomials and integers. Integers being just positive whole numbers, or I guess positive and negative whole numbers. And particularly, we're going to compare polynomial long division to what we just did, which was integer long division. All right. And what dividing a polynomial does is allows us to find factors, right? If you think about factoring a quadratic or something, right, like this, you're just thinking about what are the two things when I multiply them together give me this? Well, figuring out what multiplies together to give you that answer is really just division in disguise, right? This number is 12 times 305, right? 23 times 152 is almost this, right? That's the process of division. What two things multiply together to give you your quotient. And so what we're going to do today is on M226, and it's dividing out polynomials just like we just did with numbers, okay? So I want you to scroll to the bottom page here, this worked example, okay? Now, this is kind of crazy how they did this worked example, all right? And there's a lot of steps going on, but here's what I want you to do, okay? With the people in your group, with the people around you, I want you to try and break down this process, what they did. This is a completely solved problem, by the way, okay? Now, you did the one on the left. You just did. You divided 3,660 by 12, and you did this whole process where you, like, dropped numbers down and, multiplied things and did that. This whole process is the actual same as this, except for instead of using integers, we used polynomials, okay? So I want you to take 5 minutes or so, talk with the people around you, and just try to make sense of what's going on in this box to the right, okay? Take a look at what's happening. There's little letters to help you sort of read and follow along in order, right? And the answer that they got, by the way, is already up top right here. That's I guess 8. No, I don't know. This is the answer. And this is what you're dividing, and this is your divisor, okay? So make sense of this box. Talk with the people around you. If you're still like confused, at least just like read through the steps. Try to look like, okay, they divided x cubed by x equals x squared, and that's how they got this, blah, blah, blah. Okay, so take 5 minutes to do that. Talk with people around you. Okay, hopefully you have some idea of what's going on. The biggest trick for me to figure out is to think about, like, instead of, looking at this big polynomial and thinking about all these different, like, coefficients and variables with exponents, just think about these as the places of a larger integer, right? Your 3, your 6, and your 0, right? Each one of those is kind of just like one of these terms, okay? And so we're going to answer these questions on the next page to help us sort of analyze that. I hope you can come up with some good answers for A. Obviously, I'm not there in person to ask you. So with the people around you, answer question A. Think, pair, share. What are the ways that integer and polynomial long division, the algorithms are similar? Think about that, okay? And write some of those down. Okay, so if you have some of these ways that they're similar, here's some of the ways that I thought of. Okay, so you can match this to yours, and you might have more ways, so I might be missing something. Chances are you have a better description than I have, right? So here's how I find the algorithms that they're similar. I kind of talked about it in the last before the last break. Is thinking about how the terms of a polynomial, right, your x cubes, your x squareds and stuff, the terms of polynomials are like the places of an integer. Of an integer, right? Meaning like the hundredths place, the tenths place, the thousandths place, right? Those are like the terms of a polynomial in that you're trying to multiply in your divisor into that number, right? Another way they're similar is you go piece by piece, right? You try to get your divisor in as many times as possible before moving on, right? And so you do go step by step. And when you run out of things to multiply in, you drop something down. Right? So you try to multiply into the smallest thing, and then if that doesn't work, then you drop something down to make it bigger. Okay. You probably thought of some other ways. It is also similar in that it gives you a remainder, right? It does the actual division for you, and it gives you a remainder if there is one. So let's think about what that would mean in the context of this problem, right? So from the one that we did on the warm-up, or that first initial page, we said that 3,660 was equal to the thing I was dividing by 12 times whatever I ended up with on the top of my calculation, which was 305, right? If 3,660 divided by 12 is 305, then 12 times 305 is 3,660. So that's what I put here, 12 and 305, right? Well, similarly, from the work that they did for us, okay, we can see that I can just take the thing I'm dividing by, my divisor, and multiply that by my answer, whatever I get at the top of my little quotient, right? And so, looking back on the previous page, those things were x plus 8. By the way, I don't know if anyone noticed, there's a typo in the book. That should be a plus. Bonus points for you if you, no, not actual bonus points, like, theoretical bonus points, like whose line is it anyway bonus points. So the thing I'm dividing by, my divisor, is x plus 8. And my, what's the word? Is this the word? Is quotient this? Have I been messing up the whole time? I don't remember. Leave a comment if I did it wrong. Anyway, my answer, like what I'm actually dividing by, let me Google it. I'm actually going to be really upset with myself. What is a quotient? A quotient, oh, the quotient is the answer. Oh, it's the dividend. Oh, it's the dividend. Sorry, I got to go back. I got to do it. I got to go back. This one, sorry, I bet somebody said that. I bet Caden was like, oh, no, it's actually the dividend. Yeah, thank you. I remember. It's probably somewhere in the book, too. How do you spell it, though? Dividend. Dividend. What a word, by the way. Dividend. Okay, excuse me if I go on a tangent real quick, but can we think about this for a second? Okay, if this one is the quotient, right, my answer is the quotient, then why is this called the thing when you divide and end? Dividend. Shouldn't this be what you end with, the quotient? When you divide and end, dividend, end, right? Anyway, shout out Pythagoras, I guess. Okay, anyway, so this is actually the divisor times the quotient. Times the quotient, which was x plus 8 times whatever was left, x squared plus 4x plus 9. Okay. And that is the product of its factors, right? That is this big polynomial. Since we divided our divisor into it, and this is what we got, when we multiply those two things together, it gets me back my original thing. Okay, sorry for the cut. Here I'm answering C. Is h of x completely factored, right? H of x is our thing right here, what we just came up with. Okay, our divisor times our quotient. And so really it's x plus 8 times x squared plus 4x plus 9, right? And really what it means to be completely factored is, can you figure out all the real zeros, right? Now, on first inspection, you might think, oh no, because we have this quadratic, right? And this quadratic is, without factoring it, you can't figure out the zeros. However, if you go to look at it, right, if you're like, okay, let's try and factor this thing, you got to realize, well, it's a nice polynomial. There's a coefficient 1. And so you would just figure out what two things can multiply to 9 but add to 4, right? They got to multiply to this but add to this. And you realize after a little bit of thinking that the only ways to multiply to 9 are 3 times 3 or 9 times 1. And when you add those, you get 6 or 10, which are not 4, which means that this thing cannot be factored any further, right? There are no real zeros that this quadratic has. It lies above the x-axis entirely, right? And so I actually can figure out all the real zeros. And so it actually is factored all the way. I cannot factor it anymore because this thing has no real factors. Okay, so the only factor that I can see is x plus 8, or the only zero I can see is at x equals -8. Okay, and then D, like, because of this, we're going to end up with imaginary things. Imagine all the numbers. And so if we end up with imaginary factors, like, I don't really care. So I don't worry about D. And in this case, for E, the real zeros is what I want to figure out. Well, that just happens at the x plus 8 factor, which means if I want to figure out the zeros, I just have to set that equation equal to 0. And through one step, I can see that x equals -8 is the zero of this function. Okay. Okay, so here is our first real example of how you would use this, how you would use this polynomial long division, okay? And they give us a hint. So question number 2 is basically asking us to long divide x minus 7 into this polynomial, okay? Are you ready? Are you ready? Are you ready to do this? I'm ready to do it. Are you ready? Okay. So if you didn't get that worked example, if you felt like you were still struggling with where they were going, hopefully I can help by walking through the process right here, okay? So really what they're trying to say is solve x equals x cubed minus 10x squared plus 11x plus 0, or plus 70 equals 0, which is just our polynomial. And they give us one of the factors already. Now, if this is a factor, that means it can evenly go into this thing, right? It's a divisor of this polynomial, which means we should be able to divide this out and end up with no remainder, okay? So in other words, x minus 7 should be able to divide evenly into x cubed minus 10x squared plus 11x plus 70. Okay, so where we start is just like we were doing for our first ever, well, not first ever, the one we did today for the long division problem, okay? And what you're gonna do, okay, is try to get this divisor, you know, the thing on the outside, into the little pieces, into each of the terms of your polynomial, starting with the leftmost thing, okay? Now, the most important piece to look at is this x right here. This is the money thing, okay? This is what we're trying to get into our polynomial, right? And like this is our guiding light, okay? So in other words, when I look at my first step, my first question is, how many times can x go into x cubed? Right? How many times can x go into x cubed? Well, x can go into x cubed x squared times, right? Because x squared times x is x cubed, all right? Now, the next step, what I'm going to put right here is then the number that I figured out, the first term of my quotient, times my divisor. Okay, so I'm going to take x squared, and I'm going to multiply it times my divisor. Okay, so I get x squared times x and x squared times -7. And you end up with this. X squared times x is x cubed, and x squared times -7 is -7x squared. Okay, and now, just like we did in long division, you then just subtract this line from the top line, right? The terms in our polynomial. And so we're going to take these two things and we're going to subtract them. So x cubed minus x cubed is 0, which is good. 10x squared minus -7x squared, right? Remember, minus and negative is the same as adding. This is -3x squared, okay? So now I have -3x squared. And what we're going to do then is drop down the plus 11x, okay? And now, once again, we go back to our guiding light, the x in our divisor. And I'm thinking about how many times can this x go into -3x squared? Well, it can go in -3x times, which means I put a -3x right there, okay? And then I multiply this -3x times my divisor to get what I'm going to put underneath this row. So -3x times this whole thing. Well, my first term is going to be -3x squared, which is good. I want those to cancel out, right? I want to make my process smaller and smaller each time. However, I'm going to have to multiply -3x times -7. Well, that's going to give me plus 21x. Okay. -3 times -7 is 21. X times 1 is x. Okay. So now we take this and we subtract. Oh, that was a bad line. We subtract. Okay. -3x squared minus -3x squared is nothing, 0. Okay. But then you end up with 11x minus 21x is -10x. Right? 11 minus 21. So then last but not least, you drop down this 70. And I can already see we're looking really good because how many times can my x, my guiding light, go into this -10x? Well, -10 times, right? -10 times. And what happens then is I take this -10, I multiply it times my divisor, and I get -10x minus 70. Okay. Or, sorry, -10 times -7 is plus 70. That's good. We should have the same thing because then when we subtract them and drop a line, that means we end up with, if you take something and subtract that thing, you end up with 0, which means we have no remainder. Woo, we have no remainder, which means that we can write this polynomial as this. The thing I'm dividing by, x minus 7, my divisor, times my quotient, which is x squared, x squared minus 3x minus 10. Okay. And now they want us to find all the zeros. We know one of them is x minus 7. Let's see if there are more hidden within this. It might be factorable, it might not be. Let's see, okay? So we know we need to multiply to -10, but add to -3. I'm just factoring this like, the quick way because it's a coefficient 1, right? Leading coefficient 1. And I can see this one because -10 is equal to 5 times 2. Well, -5 times 2. One of them has to be negative, but -5 plus 2 is equal to -3. Which means my two answers are -5 and 2, which means using these, my total final factored problem is this: x minus 7 times x minus 5 times x plus 2, which means I have 3 zeros. They happen when x is 7, right? From this one, that's what happens. That's the value of x you have to make for that to be 0. It happens when x is 5, and it happens when x is negative 2. And those are my 3 answers. Those are the 3 zeros that this cubic function has. The 3 real zeros this cubic function has. Which is a lot. I know this was a lot. But it's a lot nicer than using the cubic formula. I'll tell you that much. If you remember me showing you the cubic formula real quick on, I think it was Friday. Okay, so one more problem for the day. That I want you guys to practice, which is on page M230, and it's just number 1A. I just want you to do this one. Okay, don't worry about B and C. We're going to do B and C tomorrow. They're a little bit trickier, okay? And there's a couple of things that we have to do to set it up nicer. But I think that you should be able to get x cubed plus 2x minus 5x plus 16. Divide that by x minus 4. I know they don't give you enough space here, but try to make it work. You can always sort of break your thing into 2 steps maybe. But it's going to look something like this, right? And you're going to try to figure out how many times can x minus 4 go into this polynomial. Okay, that's your overall goal. You would start off by saying, well, this x can go into x cubed, x squared times. You then multiply that, so you get x cubed. Let me make my pen thinner real quick. There we go. X cubed. And then you multiply x squared times negative 4, which would be minus 4x squared. You then subtract these, and you end up with 2x squared minus negative 4x squared is 6x squared. And then how many times can x go into that? So on and so forth, until you are left with a 0 at the total end, or maybe possibly a remainder, okay? So this one might have a remainder, or it might have a final fully divisible factor that is x minus 4. Okay, so work on this problem, try to get it, work with the people around you, and then we'll come back tomorrow, go back through this stuff a little bit and do some more practice with these trickier ones like in B and C. Okay, thank you guys for watching, and have a great rest of your day.